Hi, I'm Margie Coleman. Today we're going to work on solving systems of linear equations. What is a system? Basically, a system is just two linear equations given together that looks just like this. We have the bracket at the beginning to say that it's a system. The point is to find one ordered pair that satisfies both equations. Let's start by graphing. What we have to do is enter these into our graphing calculator and find the point of intersection. So I need to get y by itself for each equation. For the first one, if I subtract 3x from both sides, on the left I'll just be left with 2y equals, and I'll have 8 minus 3x on the right. Then I want to get rid of the 2, so I divide by 2 on both sides. That cancels, so the first function I want to enter in my calculator is y equals 8 minus 3x over 2. For the second equation, all I have to do is subtract 2x from both sides. That leaves me y equals 5 minus 2x. Now let's see what happens when we graph those on the graphing calculator. So we want to graph those two equations. So we'll go to our y equals screen. And we'll put the first equation, which is 8 minus 3x all over 2. So I have to put that numerator in parentheses. 8 minus 3x, close parentheses, divided by 2. That's my first equation. Then I'll hit enter to go down to line y2, so I can put my second equation, which is y equals 5 minus 2x. 5 minus 2x. Now I can look at the graph and see where these two intersect. I like to start with zoom standard, number 6, to get a nice, easy viewing window. And if I look at the two equations, they seem to have an intersection point someplace around here, which looks like the point 2, 1. Now I can go back and verify whether the point 2, 1 actually is a solution for this system. So from our graph, we found that the point 2, 1 seemed to be the solution for this system. To make sure that it is, we'll plug the values of 2 and 1 in for x and y in each equation, one at a time, to make sure that it works. So I will substitute 2 in for x, giving me 3 times 2, plus, and then substitute 1 in for y, 2 times 1 equals 8. And let's just make sure that that works. 3 times 2 is 6, plus 2 times 1 is 2, and we hope that equals 8. 6 plus 2 is 8, and yes, 8 does equal 8. So I have verified that it worked in the first equation, but I've got to make sure it works in both equations. So let's substitute 2 in for x in the second equation, giving me 2 times 2, plus, and put 1 in for y, 1, equals 5. 2 times 2 is 4, plus 1, we hope equals 5, and as you know, it does. 5 equals 5. So that ordered pair did work in both equations, so that is a correct solution. Now let's explore some algebraic methods for solving systems. We don't want to have to draw graphs all the time, and sometimes the graph doesn't give us an accurate answer, so we need algebraic methods. Let's start with substitution. For substitution, I start by getting one variable by itself in one of the equations, and then I substitute that value into the other equation, like this. In this case, I have a y that's almost by itself already in the second equation. So I'm going to get y by itself for this equation. Again, I just subtract 2x from both sides. So I get y equals 5 minus 2x. Now, what I've stated is that this expression, 5 minus 2x, is equivalent to the value of y. Therefore, I can use that value and substitute it in for y in the first equation, giving me 3x plus 2 times my new value of y, which is 5 minus 2x, equals 8. Now I can distribute my 2, so I have 3x, and I have plus 2 times 5 is plus 10, plus 2 times minus 2x is minus 4x, equals 8. Again, I have some like terms. 3x minus 4x is just minus 1x, so I have 10 minus x equals 8. I can subtract 10 from both sides, leaving me negative x equals negative 2. Dividing both sides by negative 1, I get that x equals 2. But that's just the x coordinate for my solution. I still need a y coordinate as well. So what we do is we take that x value that I just found and plug it back in for any of the original functions, either this first equation or this equation, or I could even use the one that I rearranged. And that looks like the easier place to do it. If I just write y equals 5 minus 2 times what I just found my x value to be, which is 2, then I get y equals 5 minus 4, or y equals 1. So my y coordinate is 1. We could verify that by plugging those the ordered pair 2, 1 back into the original equations, but we did already do that. Here's another system. X equals 3y minus 11, and 4x plus 5y equals 7. Let's try solving this one by substitution. In this case, I already have a variable by itself. X is by itself in the first equation. So I already am stating that this expression, 3y minus 11, is equivalent to x. So I can substitute that in for x, or just plug it in for x. That gives me 4 times my new definition for x, 3y minus 11, plus 5y equals 7. Now I'll distribute my 4, so I get 12y minus 44 plus 5y equals 7. Again, I combine my like terms, the y's, so I get 17y minus 44 equals 7. I can add 44 to both sides, so I get 17y equals 51, and if I divide both sides by 17, I get y equals 3. So now I have the y coordinate for my solution, and I still need x. So again, if I take this y value and plug it into my first equation, I get x equals 3 times 3 minus 11. So x equals 9 minus 11, or x equals negative 2. So my solution is negative 2, 3. Again, you can always verify that value by plugging it back into the original two equations and making sure that it works in both places. Now let's explore another method for solving systems algebraically. This is called the elimination method. With this method, the idea is to line up the two equations so that when the equal signs are lined up, the x terms are right on top of each other, the y terms are right on top of each other, and the constant terms are right on top of each other. Then we have to transform the equations in such a way that when I add them together, one of the variables cancels. Here's how that works. In this equation, I either need my x terms to both have the same number, but one positive, one negative, so opposites in front of it, or the y terms to have opposite coefficients. The x's are 3 and 2. Those aren't anywhere close together, but in the y terms, I can easily turn this y by itself into a negative 2y with simple multiplication. So that's my strategy. All I can use is multiplication. So I'm going to multiply this whole second equation by negative 2. So my first equation is going to stay exactly as it is, 3x plus 2y equals 8. But my second equation, everything gets multiplied by negative 2. So I get negative 4x minus 2y equals negative 10. Don't forget to multiply negative 2 on this side of the equal sign as well. Now everything's lined up nicely. I can add my two equations together. 3x plus negative 4x is negative 1x, or minus x. 2y minus 2y is 0, so that canceled right out for us. 8 minus 10 is negative 2, and if the opposite of x is negative 2, then x is 2. Again, I now have one coordinate in my answer. I need to find the other, so I take this value and I substitute it in for x. So I get 2 times 2 plus y equals 5. So 4 plus y equals 5. And I subtract 4 from both sides and get y equals 1. So my solution for this system is the ordered pair 2, 1, which, as you'll notice, is the same value we got when we solved it by the other methods. Let's try another system using elimination. This time we have the system 4x minus 3y equals 18 and 3x plus 2y equals 5. In this case, there's not one simple multiplication that's going to make either the x's or the y's match up. So we're going to have to do a combination, and I have a couple of options. I could multiply the top equation by 3 and the bottom equation by 4. These would both be 12s. Make one of them negative and I'll have opposites. Or I could multiply the top equation by 2 and the bottom equation by 3, and these would both be 6s. And one would be negative already because I already have negative and positive. In this case, let's go ahead and get rid of the x's. So I'm going to multiply the top equation by 3 and the bottom equation by 4, but I want one to be positive and one negative, so let's make that negative 4. So my new equations are 3 times 4x is 12x, 3 times minus 3y is minus 9y, and 3 times 18 is 54, so equals 54. Second equation, negative 4 times 3 is negative 12x, negative 4 times 2 is minus 8y times 2y equals, and then negative 4 times 5 is negative 20. Now let's add those two equations together. Again, 12x plus negative 12x is 0. Those two cancel out for us nicely. Negative 9y plus negative 8y is negative 17y. And 54 plus negative 20 is 34. And now all I have to do is divide both sides by negative 17, and I get y equals negative 2. So again, I have the y coordinate this time. To find the x coordinate, I have to plug that y coordinate back in or substitute it for y in one of my original equations. Let's take the second equation. So I have 3x plus 2 times my new value for y, which is negative 2, equals 5. So 3x minus 4 equals 5. We'll add 4 to both sides. So 3x equals 9. And divide both sides by 3. So x equals 3. So the solution for this system is the ordered pair 3, negative 2. There are a couple of special cases that we have to watch out for when we're solving systems. One is the case where the lines are actually parallel. As you might remember, parallel lines never intersect. So we'll never find a solution if the two equations give me lines that are parallel. In this case, both equations have y by itself, so they are in slope-intercept form, meaning the coefficient of x is the slope. Notice the slope of the first equation is 2. The slope of the second equation is also 2. So that verifies that these are parallel lines. So I can look at it right now and say there are no solutions to this system. But let's take a look just to be sure. Let's graph them and make sure that they look parallel. So I'll go to y equals. And for y1, I'll put my first equation, which is y equals 2 2x minus 3, and I'll hit enter to go to y2, where I'll put my second equation, y equals 2x plus 2. Again, let's get a nice standard viewing window at zoom number 6. And we can see that these two lines seem to be parallel. And since we were sure of it because of the slopes from the equations, that's how we know that there are no solutions to this system. So we noticed they had the same slopes, we graphed them and they looked parallel. Now let's see what happens if I try one of my algebraic methods. In case I have a situation that's not so obvious, how will I know when I have parallel lines? I'm going to use substitution in this case because I already have y's by themselves all over the place. So it'd be just as easy to take this definition for y and plug it into the y in the other equation. We'll just substitute it right in here for y. So I have 2x plus 2 equals 2x minus 3. Now I want to solve for x. Whenever I have x's on both sides, it's always a good idea to try to get them together right away. So I want to get rid of the one on the right by doing minus 2x. And what I do on the right, I do on the left, minus 2x. 2x minus 2x is 0. 0 plus 2 is 2. 2x minus 2x is 0. 0 minus 3 is negative 3. I'm left with an equation that says 2 equals negative 3, and we all know that that is definitely false. Whenever I use a valid algebraic method to solve a system, and it leads me to an equation that has no variables left anymore, and it's just simply a false statement, that is a key that there really are no solutions to this system. And as we just discussed, that means that this particular system contained parallel lines. The other special case is the situation where the two equations really represent the same line. In this case, I have x minus y equals 4 and 3x minus 3y equals 12. And you might notice if I multiply the first equation by 3, it exactly gives me the second equation. They definitely are the same line, written in two different looking ways. Now I could graph these lines, and all that you're going to see on your graphing calculator is one line on the screen. You won't even be able to tell because the second one's just sitting right on top of it. But let's solve algebraically so you can see what that looks like. So I don't have any variables matching up, but my x's can match easily if I multiply my top equation by negative 3. So I'll do that. So negative 3 times x is negative 3x. Negative 3 times negative y is plus 3y. Negative 3 times 4 is negative 12. And then my second equation says 3x minus 3y equals 12. When I add these together, negative 3x plus 3x is 0. 3y plus negative 3y is 0, so all I have left is 0 on the left side. Negative 12 plus 12 is 0. Again, my variables just went away on me, but this time it left me with a true statement. That means no matter which value I choose to put in for x, if I work everything out, I'm going to get a value for y that'll make it true. So there are infinitely many correct solutions. Specifically, every point on that line is a solution for this system, and there are infinitely many points on any one line. Now let's try an applied problem. Sometimes you get a mixture problem, particularly in a science situation, that looks something like this. How much pure alcohol do I need to add to 2 liters of 30% alcohol solution so that I'll have a 65% alcohol solution? For me, I need to get a drawing. I need to get a picture that kind of helps me organize my thoughts. So let's just try that. With mixture problems, it's nice to think of this as being 3 beakers. In the first beaker, I have 2 liters of a 30% solution. That's what was given. In the next beaker, I have my pure alcohol, which is basically a 100% solution. And whatever I put in the second beaker, that's what I'm going to mix with the first one to get my combination. So I don't know how much I'm going to use there, so I'm just going to call that x liters. That's one of my unknown amounts. Now what happens is I take these two beakers and I dump them together. So I add them together, dumping them into the third beaker. And what I want to be left with is a 65% solution. And I don't know how much I'm going to have all together, so I'm going to let that be another unknown. We'll say that's Y liters. Now I'm going to write two equations. The first equation comes from the total amount of liquid in each beaker. The first beaker has 2 liters, plus whatever's in the second beaker, which is X liters, and that will give me whatever's in the third beaker, which is Y liters. The second equation comes from the amount of alcohol that I have in each beaker. The first beaker is 30% alcohol, so 30% of 2 liters. So 0.3 times 2 is the amount of alcohol in the first beaker. In the second beaker, 100% of the liquid in that beaker is alcohol. So the whole X liters is alcohol. My final solution needs to be 65% of the Y liters that are there. So I have 0.65 times Y. And I can simplify this second system a little bit. 0.3 times 2 is just 0.6 plus X equals 0.65 Y. And again, my first equation is 2 plus X equals Y. In this case, I do have a variable by itself. I have a Y by itself. So I'm going to use this 2 plus X and substitute that in for Y in my second equation. So I get 0.6 plus X equals 0.65 times my new definition of Y, which is 2 plus X. And let's start by distributing the 0.65. So I get 0.6 plus X equals 1.3 plus 0.65X, just distributing my 0.65. Now I'm going to subtract 0.65X from both sides because I want to get my X's all together. So on this side, I have 0.6, and then I have 1 minus 0.65, which is plus 0.35x, equals, and over here, the 0.65 minus 0.65x's go away, and I'm left with just 1.3. Now I can subtract 0.6 from each side, and I get 0.35x equals 0.7. Divide both sides by 0.35, and you'll probably want to do this in your calculator. 0.7 divided by 0.35 equals 2. That's the x coordinate for my system. But notice, the x coordinate in my system is the amount of liquid that I'm going to need to use in the pure alcohol beaker. So that is the number of liters. 2 liters of pure alcohol is what I need. And that's really what the question asked, so I can stop there. If I want to know how much alcohol I'm going to have altogether in the final beaker, or how much solution altogether, I can take my first equation. I have 2 liters of liquid in the first beaker, plus I just found I'm going to use 2 liters in the second beaker, and that means that the amount of liquid I'm going to have left is 4 liters. So I will have 4 liters of 65% alcohol solution in the final beaker. In summary, today we talked about solving systems of linear equations. We used 3 methods. The first method was graphing, where we graphed the 2 equations and found the point of intersection. The second method was substitution, where we got one variable by itself, then we substituted that expression into the other equation and solved. The third method was elimination, where we tried to get one variable to have opposite coefficients in the 2 equations so that when we added the equations, it canceled, and then we could finish solving.